Very. You get it? I'll begin with a word of prayer. Dear Father, we thank you for this day, and again for most of these students to pray with us today. Help us to add understanding from this time and just prepare for the final, Lord. In your name I pray. Amen. Let's see here. Yeah, I do need your take-home test 3 solution now. That is true. Let's see here. If you haven't turned it in already. Where was that? Is this it? This is it, right? Yes. All right, let me just kind of let's just take a step back here, just big picture. Because one of the things I wanted to address today was, this is a take-home test, so there's always kind of a question. As you're thinking about the final, I always tell people to review the tests for the sake of the final. And, that's not it, but that's a good starting point, among other things. I would say the smartest thing, if I was a student, and I wouldn't usually do this because I don't know, I think we just have a natural tendency to focus on what we already know because it makes us feel better, right? But of course, what you actually should study is whatever you got wrong, because that's the thing you need to fix, right? But anyway, as I think about this take-home test, things that stick out to me just right off the cuff, number one is obviously something that could have been an in-class test, would have been totally reasonable, right? Number two, there's got to be a way to make this problem less writing to make it an in-class test. In its current form, it's a little bit kind of heinous for an in-class test. Number three, number two is actually very, very easy if you understand the machine that you're supposed to use to do it. But if you haven't yet learned the machine, then yeah, it's pretty awful. See, I look at this matrix and I immediately recognize the real Jordan form for eigenvalue 3 plus or minus 4i. Well, really minus 4i. And so I know that E1, E2, E3, E4 are real and imaginary parts of a pair of generalized complex eigenvectors. I can see all that from just looking at that. So if you know that, then you can use it to construct solutions.
If you're halfway there, then you have to understand proposition 9.6.1.
We have to do what?
Then you have to understand the proposition using the magic formula.
Proposition using the magic formula, yes, also that. That is also true. Now, number three is a decent test question, but, does it have to be on the fifth order polynomials? Sure. No, there's a version of this that is like less awful. I can make it a second derivative and make it, cubics or something. Then we got, 4x4 matrices instead of 6x6 matrices, and it really tests the same concepts, right? So this is a little bit egregious for in-class test in its current form, but there's something there to learn. Yeah.
Back on 2, we were kind of confused on how it's 3 minus for both.
Yeah.
How do we know that it's 3 minus 4i?
Oh, well, we had well, we worked out that if you have a times a plus ib equals to alpha plus I beta times a plus ib, a theorem we had was that if you look at basically this thing, I'm writing the theorem in a different format than we wrote it, but this is ultimately what the theorem said, is that this similarity transforms A to a rotation dilation block, which is in particular alpha. I think the minus beta is down here, beta, alpha, like that. Okay. For example, A is equal to alpha A minus beta B, and this is from the real part. From the imaginary part, you can say that A times B is equal to alpha B plus beta A. So like when you choose a basis, essentially that's A and B, that gives the first column being that, and that gives the second column being that. So working backwards, I can see eigenvalue.
Yes.
I can see eigenvalue 3 minus 4i there. I wasn't meaning to make it tricky. If I had to do over again, I might have written 3, 4 minus 4, 3 instead. So, but whatever. That's a minor point here. 4, find the minimal polynomial A is a decent test question. calculate e to the ta, that's kind of more trying to separate my low a's from high a's kind of question. I mean, it's a little bit out there. That's actually not that bad. I'll show you in a second. This is definitely a test question in class, could be. Although I would like to see eigenvalues which are a little bit less cluttered than these ones, right? This had not integer eigenvalues, right? I mean, on the other hand, if you look at the matrix, it's 1, shnikes. I may have done that wrong. 1, 2, 2, 0 is the matrix of this form. So the trace of it's 1, right? So the sum of the eigenvalues is 1. But, whatever. This one definitely would make a decent in-class question. That's pretty relatively, that's, you know, I can't have 10 questions like that because it's got some computational teeth to it, right? I mean, like, to find an orthonormal basis, to find a basis, if I delete the orthonormal word here and say find a basis for S perp, that's a very reasonable, straight down the middle kind of question, right? Because all you got to do is calculate the null space of the transpose of the matrix of S, which should be fairly straightforward.
Gram-Schmidt's the long part of that.
Yeah, the Gram-Schmidt is the part that stings. Then this guy down here, parts of this are reasonable, right? Like, certainly to ask, is T in the dual space? That's a reasonable test question. I mean, I would like you to know what the dual space is, what its definition is, you know. And I think this B is also a reasonable test question. I don't expect you to memorize the definition of the sharp and the flat. So if I have a question about musical morphisms, I will remind you their definition, okay? But, you know, there might be a question on the final that's prove that sharp or flat is an isomorphism. That's actually not a bad question that I didn't ask you. That was homework last year. This part C is probably not a good test question because it's just, well, I don't know. I think find C in its isolation is a decent test question. Like, what's the matrix? It's actually kind of interesting. It's just basically 6 relatively easy integrals that you have to calculate, right? And then you figure out what the matrix is. What would be slightly unfriendly was to actually make you do this, because then you have to invert a 3 by 3 matrix, which, you know, that's, well, I mean, you can do it, but this problem in its entirety would be a significant time allocation on my final, right? Let's see here. This one, find an orthonormal basis. I think it's a difficult problem, but it's reasonable.
This is one where you don't want to use Gram-Schmidt.
Yeah. Yeah. I might find better closest vector questions for the final that are a little bit not as calculationally encumbered as this one. Not too many of you are going to get to the end of it if I was to ask this on a test, right? Because there's a lot of calculational stuff in the way of you getting to the answer here. Prove the third isomorphism theorem. I don't think that one's actually too bad. Rotations in R3. But I might find I don't know. I mean, that's a reasonable question, but maybe I could find a better one. I don't know. Here, I probably would typically just test on, I'd probably invent a question which is basically testing if you've actually worked through this. There's a variety of different test questions that are spurned from that angle. Like, the most obvious one is just asking a question like C again, you know. But anyway, so I guess that was kind of boring. I just basically told you it's all reasonable. Sorry about that. Certain parts are less, you know. I think the part A and B here, parts of that are really kind of tricky for an in-class time pressure test, because there's some things about just products of complex numbers and real numbers, which are subtle things, but they're not exactly linear algebra either, are they? They're something else, but they were impactful for your thinking there. So. Now the question is, I have worked these things out before. The question is, can I find them? Let me see if I can find it real quick. I had hoped, of course, to actually have the full solution here to look at with you. But then there was this thing called a math party this weekend and other things, and I've gotten... What? Yeah. You know what I'm talking about. You heard it was what? Let's see here. So this was so if you guys don't mind, it would help me out a lot if I could just post the 10th homework from last year, because there's a couple of the problems in your homework are in there, so you can just kind of focus on those ones if you don't mind. Like, let's see here. Which ones were in your take-home test? Problem 164. Oh, look, there's a second isomorphism theorem. Yeah, some of these were in the homework. I didn't assign 166. Let's see here. What else did I do? You did solve Gwyneth's musical morphism problem, and problem 171 was also in your homework. Anyway, these are not bad problems. I don't know if I should really post this or not. I think it may be distracting to you, though.
Did you choose to call them musical morphisms instead of musical isomorphisms because alliteration?
I don't know the answer to that question. I'm not sure that the terminology is mine.
Because Wikipedia says isomorphism.
Oh, yeah? Well, if Wikipedia says it, I guess that's the final authority. Let's see here. This is the third isomorphism theorem, right? So here's the proof. Let phi go from the quotient of v by u to the quotient of v by n be defined in the natural way. So we just say phi of v plus u is phi of v plus n, or in other words, phi of x plus u is x plus n. Is this what is it? Is this the right one? Okay. So I feel like I should at least pause and is it well defined? How do I know that? How do I know that this is not ambiguous? Because I'm using a coset to define the formula. How should I know that that's actually even well defined? I would pick at my solution a little bit here. Think it's something missing, right? Well, notice that u is a subset of n, right? So that goes to show you that. Let's see here. How can I say this? I have to have the same representative. More to the point, if I had x plus u equal to y plus u,
And you showed that.
it would. Oh, did I? Oh, I felt guilty down here finally. Is it a function? I mean, I've checked linearity before. I've checked if it's a function. That's kind of bad form, right? Oh well. But thank you, Sam. The point is, if the inputs were equal, that means that the difference is in u, which is a subset of n, which means that phi of x1 and phi of x2 are equal. All right, they give you the same coset. So it is, in fact, a function. It is, in fact, linear. Here's the proof of that. And what else do I need? I think that's all I need. I need linear, and I need this actually well-defined function. Then I can apply the first isomorphism theorem to that, right? So to apply the first isomorphism theorem, then I have to calculate what's the kernel of this map, right? So what's the kernel of this going to be? I look at basically x plus n equal to 0, which means what? That means x, yeah, essentially x plus n is equal to n again, right? Eventually I'll get around to that. I think at the moment I'm showing it's surjective. Oh, I'm just claiming it. It's fairly obvious that it's surjective, though. I mean, if you don't, you can prove it. You give me your favorite thing in, where are we? V mod n. Pick anything. What do you want? How about x plus n? I'll map to it. Phi of x plus u is equal to x plus n. There, we're done. Surjective. Okay, that was exciting. But it's clearly surjective, is the point. And so then the kernel is these, like you guys were just telling me, mapped to 0, but 0 is n here. And you told me like 2 minutes ago that x was in n. Very good. And so what that means then is what? Well, x is in n, right? So we're looking at the cosets with representatives from n mod u. That's n mod u. So first isomorphism theorem says that the domain of the map mod its kernel is isomorphic to its range. In this case, the range is the codomain, and there you have it. That's the first isomorphism theorem, which is, roughly speaking, that you can cancel fractions in terms of linear algebra notation. Right? I don't know. Okay. Interesting. There's your homework problem. You've seen that before. Here's one that I thought was confusing, so I didn't give it to you guys. Was there anything else in here? I think that was it, wasn't it? Well, this one I've already published the homework solution for, right? I actually rewrote a new solution for this, but here's my old solution. Is a better one. I don't know if I should be like, hey, or like, well, they're both my solutions, so I guess I can take the criticism / compliment. Uh-oh.
About 174, the matrix of G star is not really G inverse of G, but the transpose inverse of G.
You disagree with my solution for G star?
Yeah, the matrix of G star.
Now, are you disagreeing with the solution I posted or the one we're looking at right now?
No, the result of the matrix of G star. I see in your solution on the blackboard.
But the thing is, it's symmetric. So you said it was the transpose of my answer?
Yeah, it's the matrix of G star is transpose of G inverse.
But that's the same thing.
Oh.
I mean, the matrix of G is symmetric. I think the matrix of the inverse is also symmetric. Is the inverse of a symmetric matrix symmetric? That's a good question, actually.
It should have to be, because you could find something about,
That's a decent question for the final, right?
Using row reduction to find the inverse, it would have to be symmetric.
All right, let me put this away here.
But is n symmetric?
So this one was that problem. Problem 145 I assigned you guys, didn't I?
Yeah. That was the one with the
And 150 was homework. 152 was homework. 153 was homework. So it's not all of these you've been assigned, but a lot of them. Let's see here. The one I wanted to look at was 145. So this was I talking about. It's a relatively simple problem, but just numerically it was a little bit, not super happy about my non-integer eigenvalues. I mean, admittedly, you guys do know real numbers. Like, I don't just have to use integers with you, right? But it just feels better when I have integer eigenvalues. I don't know, just personally. Stephen agrees. Anyway, here's the details, the somewhat awful details of how to find eigenvectors. This is the unit eigenvector with eigenvalue, what was it, 1 plus root 17 over 2. And down here I will find the unit length eigenvector with eigenvalue 1 minus the square root of 17 over 2, right? And this u1 and u2 are perpendicular. They form an orthonormal basis for R2. And with respect to that coordinate change, we get this x bar and y bar in terms of x and y. And so if I solve these, well, there's the coordinate change, but and if I actually solve for x, if I replace x and y with x bar and y bar, I would actually get this formula, right? As it happens. So there's your formula in eigencoordinates for the quadratic form. And geometrically, if I have x squared plus 4xy equal to 1, what you're looking at is a hyperbola. See, because that's negative and that's positive, so you're looking at something plus squared minus something squared equal to 1. This is a hyperbola.
The only downside of the
Rotated.
is that it's hard to see just whether it's
Yeah, exactly. So, anyway, I will try my hardest if I ask a question like this on the final to make the arithmetic easier, okay? is a take-home, so I don't feel too much regret, but still, you know. Look at that. At least this didn't happen, right? Did I assign this one to you guys? I think I did, didn't I? Yeah, that's another one. Yeah. All right, let me stop this and go over. I did solve the first few problems in take-home test 3 already. So like here's the proof of 1. But I think I suspect, does anyone, I mean, so the point is if t is linear and invertible, right? First of all, it means that lambda cannot be 0, right? So that's one of the things we should have argued. Lambda cannot be 0. If lambda is 0, that means that the kernel is non-trivial. If the kernel is non-trivial, the function is not injective. If the function is not injective, it's not invertible. So lambda cannot be 0. I don't have to tell you that. That is logically implied by the invertibility of t. Now, once we have that, then I just take the eigenvector equation, right, this guy, and calculate by, t inverse on both sides. That gives me t inverse of t of v is equal to t inverse of lambda v, but t inverse is linear, right? So I can pull the lambda out, and that gives me v is equal to lambda t inverse v, but then, again, lambda is not 0, so I can divide by it. And so I get t inverse v is 1 over lambda v, which goes to show you that v is, in fact, an eigenvector for the inverse of t with eigenvalue 1 over lambda. So there's that. Oh, yeah? Okay. Number 2 is kind of awful. Let's go on. Number 3 is reasonable in its way. So, just pick any basis you like. Personally, I like this one, and that gives me A. Once I have A, it's easy to calculate the characteristic polynomial because, you know what, this is triangular. I mean, upper triangular, right? So the eigenvalues are on the diagonal, 0, 0, 0, 0, 0, and yet again 0. So very boring. 0 multiplicity 6. It's pretty obvious that the eigenvectors here are e1, e2, and e3, right? Because if you set this equal to 0, calculate the null space here, it's going to force the last 3 components of your vector to be 0, and it's going to leave the first 3 free. That is entirely unsurprising when you trace back what that means in terms of polynomials, because of course 1x and x squared are killed by the third derivative, right? So these are eigenvectors with eigenvalue 0 for the third derivative operator. Yeah.
Is it okay if, like, on my solution to this, I kind of jumped to that and just said, like,
oh yeah,
these
yeah,
all are eigenvectors because of
absolutely. I don't think the matrix is necessary here, but it would be helpful if I was doing something more complicated, like say f of 0 plus f prime of 2 is my operator. Something else, like we had where I asked you to work out the problems in the homework. I asked you to work out the problems in my notes in the homework, which was rather silly because, like, my notes have complete solutions, right? So I was just asking you to work through the solutions. It was confusing to some of you. Like, what's he asking? The full solutions here. Is this real? What is this? I was just trying to get you to read those examples carefully. That was my fairly obvious intent. Well, maybe it wasn't obvious. I don't know. I guess you're used to homework being so, like, awful, and then all of a sudden I give you a gift. It's like, is it a bomb? Like, I mean, what is it, right? So it wasn't a bomb. It's here. So anyway, those are my eigenvectors. That doesn't really help me too much, but I also have in mind that homework problem, right? So I already kind of had an idea what I was going to do. Then I just need to look for sort of generalized eigenvectors of highest weight, right? So for this one, it's fairly obvious I should look at x to the 5th. And if I say t of x to the 5th, I get 60x squared. Of course, 60x squared goes to 0. So at this point, I've used x to the 5th and x squared in a basis. The next thing would be x to the 4th, right? That goes to 24x. That gives me the next two things in a basis. Then at that point, I'm still left with x cubed. X cubed differentiates to 6. I mean, thrice differentiates to 6. And so there you go. My Jordan basis would be this, and that gives me these 2x2 Jordan blocks, 3 2 chains. So, yeah. Again, wouldn't be surprised if I asked a question like this, which was much simpler, but the same idea. Like the ones that I asked you to work through in the homework, right? They were in the notes, yeah. Something more along those lines, maybe. So here, if you work it out, you get lambda minus 2 cubed is the characteristic polynomial. Then the Cayley-Hamilton theorem says that if we plug in a into that, it will work. In other words, it will get back to 0, right? So I know that if I put in a minus 2i cubed, I know it's going to be 0. That's a theorem. That's worth knowing, right? It's Cayley-Hamilton theorem. And so, uh-oh, battery. Uh-oh. Battery. Huh. I guess I better talk fast. Make my screen dimmer. There we go. Anyway, the point is that a minus 2i cubed is 0. So this also shows you that that characteristic polynomial is the minimal polynomial, right? One of the theorems that we talked about a little bit was that the characteristic polynomial and the minimal polynomial, they share the same factors, right? The same zeros, or the same irreducible factors if you're working over the reals and you have like a complex eigenvalue. But anyway, so the minimal polynomial here is the characteristic polynomial, and
The negative of it.
what's that?
The negative of the characteristic.
The negative of it, right, because of my stupid conventions, thank you. So anyway, then I use the magic formula basically to take the exponential and rewrite it as e to the lambda t plus I times t minus a lambda I plus t squared over 2a minus lambda I squared plus da 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 da. And this stuff will be 0, and these are just explicit matrices which I add together here. So, yeah. Again, we talked about that already, and that's where I got to because I was trying to listen to Dr. Long talk in the math thing earlier. Sorry. Where were we? Is this it? Ah, the rotations problem. Let me see if I can't find that right quick. We didn't look at the 8 solution yet, did we? I know it's in here somewhere. It's not the first year I've assigned that problem. I think it's a neat problem. It's kind of hard. Yeah, 136, 137, 138. Let's see here. So first of all, 136, I'll be brief here. And I think I added that theta was not a multiple of pi, didn't I? Makes your life a little bit easier. Because here I had to separate out if theta is n pi, we either get the identity or minus the identity, right? Anyway, so if theta is not n pi, that's where we should really look at. Then the only real eigenvalue, lambda equals 1 is the only real eigenvalue, which you can see from this up here, right? Because this is an irreducible quadratic when theta is not a multiple of pi, integer multiple of pi, so lambda equals to 1 is the only real eigenvalue. And consequently, E3 plus or minus is the, well, a scalar multiple, non-zero scalar multiple of E3 are the eigenvectors with eigenvalue 1. All right, to the greater. If students assume theta was not in pi z, then give them full credit. That was my intention here. All right, yes. See how nice I am? Let's see here. Sorry, I digress. So suppose R is an SO3, R is not the identity, R is only 2 eigenvectors unit length for which lambda equals to 1. So R in SO3, we have R transpose equal to R transpose R equals to I. That means it's an orthogonal matrix. And this is where the S comes in. This is special. Determinant R is equal to 1. Sorry I didn't say that to start with. My bad. Now, this tells you that the transpose is the inverse, right? And by the way, so what's that mean? Well, the transpose, here's a nice theorem for you. The matrix and its transpose have the same eigenvalues. Something worth knowing. So transposition doesn't change eigenvalues. Right, the characteristic polynomial is built from a determinant, and when we take the transpose of the determinant, it doesn't change it, so yeah. So the matrix and its transpose have the same characteristic polynomial, hence the same eigenvalues. So this says that our inverse and R have the same eigenvalues. And so likewise, if R has complex eigenvalues, lambda 1, lambda 2, lambda 3, then R inverse also has complex eigenvalues, 1 over lambda 1, 1 over lambda 2, 1 over lambda 3. Thus, the spectrum, the set of eigenvalues, has to be equal to itself under inversion in the complex sense. So without loss of generality, you can suppose that lambda 1 equals to 1. I mean, that is always an eigenvalue. If you look at the characteristic equation, we always have lambda equals to 1 as one of the solutions, right? Then the question is, what happens to 2 and 3? Well, 2 and 3 have to be the set of eigenvalues, lambda 2 and lambda 3, have to be equal to 1 over lambda 2, 1 over lambda 3. So if you think about what that means, either lambda 2 is equal to 1 over lambda 2, and lambda 3 is equal to 1 over lambda 3, or vice versa, right? Now, so if this is the case, then lambda 2 squared and lambda 3 squared is both 1. So that means that lambda 2 is plus or minus 1, and lambda 3 is plus or minus 1, if they're real. But if lambda 2 and lambda 3 are both 1, that gives you back the identity transformation, which we've forbidden. So that can't be the case. On the other hand, if lambda 2 equal to 1 and lambda 3 is minus 1, then the product of the eigenvalues is minus 1, which is also not possible. All right. So the other possibility, of course, is that they go flippity-floppity. I mean, in other words, the reciprocal of the eigenvalue 2 is 1 over, well, the reciprocal of the third eigenvalue is the second eigenvalue, and vice versa. I mean, if you have this, you have that, right? So that's the other possibility, given the combinatorics here. And so we find either that lambda 2 is equal to 1, lambda 3 is equal to 1. Again, so that's not possible if we want R not to be the identity, which means that we must have a complex eigenvalue for 2 and 3 is what that means, right? And the complex eigenvalues have to be such that they're reciprocal, which means that one is e to the I theta, one's e to the minus I theta. Anyway, the bottom line here is it says that there's no other real eigenvalue. That's what that argument gives us. And so we just have the one eigenvalue 1 and its eigenvector. So plus or minus that, our eigenvalue, normalize it, minus that unit vector is also an eigenvector with eigenvalue 1. And those are your two unit eigenvectors, which correspond to unit vectors in the direction of the axis of the rotation. Anyway, yeah, that one's kind of touchy. So then 3 here, if we have an SO3 matrix and the trace is 0, well, I know that if it's an SO3, it has eigenvalue 1. The other pair of eigenvalues, if it's not the identity matrix, right? By the analysis in the last problem, I know that I have one eigenvalue of 1, and my other 2 eigenvalues are complex. And they're conjugate pair, right? So those don't give me real eigenvectors, but I have my one real eigenvector. And so I can set up a coordinate system, right, in which the third coordinate direction is along the axis of the eigenvector, and then I just pick the real and imaginary parts of my complex eigenvector. That will give me, by the theory here, a perpendicular set of real vectors. And so what I'm trying to say is that you can basically change coordinates so that it's like part A. And so given that the trace is invariant from here to here, the trace of this is the trace of that, but the trace of this is 2 times the cosine of theta, so we can figure out the angle of the rotation from looking at just the trace of the matrix. The trace of the matrix will be 2 times cosine theta plus 1. You know. Admittedly, I could give more details here in terms of how to set up the coordinate system and everything, but you can make this argument that there exists a system of coordinates where the matrix of the rotation, the matrix of the transformation with matrix R becomes the matrix which was given in part A. All right? There exists a basis for which you can. So L R is RV, right? So I'm saying that there is a basis such that this matrix is equal to cosine theta minus sine theta, or is it sine theta? It's sine theta, isn't it? Minus sine theta, cosine theta, 1, like that. And my claim, furthermore, is that that basis actually is like the real part of the eigenvector, the imaginary part of the eigenvector, and so this one's got RU3 equal to U3 again. And these two are the R e to the I theta equals to e to the I theta U1 vectors, which exist from our analysis in the previous problem. My claim is that if you use that basis, you get that matrix. But then the trace is invariant, so we can figure out the angle of the rotation. So, that is by far the hardest question I've asked you this semester, without a doubt, right? It's a seemingly innocuous question, find the angle by which this rotation rotates, but I found this to be very challenging before I knew this line of reasoning. The last problem at the end of the first mission, pretty tough? Yeah. At the time. A smiley face, yes. Okay, let me stop talking about this problem. Let's go back and let's look at let's think about our existence, yeah? Where are we? We're in linear algebra, right? There was things before test 3, weren't there? Yes. You remember those things. Like, this is your life. Let's see here. Where were we? Test 1? We had test 1 here, didn't we? I feel like we did. Our grades are based on effort. Did I just hear that? Yeah, the final exam is going to be, like what? It just was one question. What do you think your grade in this class should be? Yeah, that's not happening. Let's see here. Oh, okay. By the way, before I forget, yes, I do have a mission to give back to you. This is mission 10, I believe. And while I've got you guys here, he says that there's, oh man, he claims there's an error in my solution to problem 129. Oh, that's it. What is it? Maybe he told me. Oh, shnikes. What happened here? 2x squared plus 4y squared plus 6z squared plus 8xy plus 10xz plus 12yz. What? Why does he have a completely different quadratic form than me? What happened here? Where did I get this quadratic form from?
From the adjacent problem.
Is that it? Oh, yeah.
I screwed them up a couple times before.
Oh. Well, that was dumb. Ha! Look at that. So, what on earth? Wait, well, that's crazy because how on earth did I get different eigenvalues in 129 and 130 solutions? I've got the same quadratic form. When I use technology, I somehow get 1, 3.54, and 10.46. When I work it out by hand, I somehow got 1 and 10 as eigenvalues. What on earth? All right, something is askew with the solution to 129. Let's just say that, all right? Sorry about that.
Is it like the bus?
What's that? Miranda? Elizabeth? Tyler? Stephen? Let me go back to test 1 here while we're... All right, so, Stephen in the back. Samuel. Hannah, purple. Darkness. Emily. Wait a minute. Emily. I know. Well, in my defense, it was the next one. That's what it was. There was a reason for it. I know that Emily's over here. I know that. Yep. Mackenzie's behind you. Zachary is still here. Oh, sorry. I'm about to give you 2. Probably just want 1. Hand that back to King. Isaiah, Tim Schneider. Tim. He's no existing. Jonathan.
Can we just retake test 1 and 5?
Tim. There's more than one Tim. Tim S, I think is, well, they're actually both S's. You're both Tim S, actually. Stephen El Presidente Thomas. Mr. Tran. Sabrina. Here you go. All right. All right, so let's just take a couple minutes here to glance back through test 1 right quick. So that was mission 9. I don't seem to have. Did I give 9 back?
No, you gave 8 back.
Okay, so I'm still waiting for things to come back from the graders, obviously. Yeah. I should hopefully have them soon, and I will let you know where you can get them when I do. Maybe I'll leave them in Sprano's office or something. Would that be helpful? If I put your solutions in Sprano's office to pick up? He always leaves it open, and he's got these shelves that's a convenient place for me to stick something. There's really no decent place for me to put it in my office. Well, not seeing certain students is a bonus. I mean, that's true, but Hannah's making me seem like a monster. Let's see here, yes.
You could leave them in your mailbox.
Leave them in my mailbox. But then people turn stuff into my mailbox, which is, yeah. As you're going into Dr. Sprano's lair, you know, he's got this sort of like fort that he's built with bookcases. So on the immediate right-hand side, I will make I know where I can put them. I'll put a sign that you can't miss, all right?
With duct tape?
Okay, so my battery's almost out. Time is slipping past us into the future, as it will. So calculate A inverse is still a good question. It's still a good question that is more fun to ask when it's attached to a musical morphism question. Now, I would remind you that there is a simple thing here you can do after you've done such a question, which is to check your work, which is to multiply it and see that you get the identity, right? And if it doesn't work out to the identity, what should you do?
Move on, you're out of time.
Yeah, you might be out of time.
Move on, you're out of time. I give up. All right. I was going to say you should try to fix your mistake, right? And so now in that sort of situation, it's completely fine to just put like one big line through it and say on the back. It may be helpful to you to do it that way rather than erasing it, because if you erase it and then halfway through I collect the test, then you get no credit, right? So something like that, where you've invested so much time in a wrong calculation, it might be wise to work on the back your next attempt. Okay, what's this one? You got A, you got B. Calculate the reduced to echelon form of the coefficient matrix, that, and state the solutions, if any. Yeah. Huh. Interesting. Oh, so here basically I'm like, well, I already found A inverse in the previous one, so I can just solve it. And so I know that that's going to work out to that, so I don't actually have to do the row reduction, right? Most of you did not do it this way. You did the row reduction again in 8-10 minutes of your time for that. Let's see here. Make it bigger. You got your vectors, you know, which is in the span of which. Typical questions, good question. A, B transpose is B transpose, A transpose. This is a problem that all of you could have gotten right, but many of you had started to study this idea, but had not finished studying it at the time I asked this question, right? You've learned it now? All right. I should ask it again exactly. Yeah.
See the improvement. Yes.
find conditions on A, B, C, D such that this is in the span. All right, this should by now be, I mean, really, if you go back and look at test 1, I don't think there should be anything here which is terribly, these problems should be easy to you by now, right? Comparatively. Elementary matrices, you might be rusty on what an elementary matrix is and how it works. You probably should look at that again. Questions about symmetric and antisymmetric matrices make great, quick test questions, right? Because if you have clear in your mind what symmetric and antisymmetric is, you can answer these questions in like 2 minutes, right? Determinant calculation, always fun. If you know the blocks, it's helpful. Let's see here. Oh, solve a linear problem. This one here is really, this is a weird question. Like, you can blame Math 221 for this. This is where that's coming from. Math 221's got me looking at weird problems that are like this. So I thought I'd ask you one for kicks. See how you do.
Your battery looks conserved.
Uh-oh, my battery's conserved.
30 minutes.
30 minutes, I think we're good. 1 minute, we got 5 minutes of class time. Where you been? If patterns persist. State and prove the column correspondence property, something that would be good if you could do, but I wonder if you could. And, you know, true-false questions about linear independence and spanning are very telling to me, whether or not you've actually understood the basic conceptual core of this class. Don't count these questions out. They're important. And one of Dr. Skambordis' pet peeves when he teaches linear is he gets to the end of the course and he asks some simple question about linear independence, and students just tell him unadulterated garbage on the final. You know? So it's very usual to be asked basic questions about linear independence and linear dependence. You know, just because I have 3 vectors doesn't mean I have a 3-dimensional space from their span, right? We need linear independence to get a 3-dimensional span and so forth. I mean, there's these ideas about dimensions and spans and linear independence. You should think about this if you haven't. I think you've thought about it. Oh, here's a block matrix, just a plain old block matrix problem. So the other test. So I mean, you know, is there going to be a subspace question on the final? I mean, most likely there will be, right? Will I ask you to find the basis? Will I ask you to find the basis of a subspace? Find coordinates of a vector. These things seem very likely, right? Find the matrix of a linear transformation with respect to a pair of bases. This seems very likely, right? I told you guys, I mean, I tell every class now and forever, it seems like forever on, that this is the problem that made me not give anyone an A one semester, that no one could solve this. It offended me. I'm sorry, but like, come on. That problem. You know, things are, for column vectors, things are very nice. Know about those things. In particular, the coordinate, you know, we take the basis matrix inverse times the vector. That gives me the coordinates with respect to this. If the basis is orthonormal, well, how does this become even nicer?
You just take dot products.
We just take dot products, right? Now, as you're thinking about the last arc of the course, you should think about easier homework questions too, right? Like as I think about the final exam, one of the things I'll be looking at is the last few missions we've had. Just kind of, we've had some nice, simple questions about inner products and things in there. There's some good test questions to be seen in there, maybe even more so than the take-home test 3. Intersections of subspaces, something I might test on. I won't like grading it, but it's something I might test on. Let's see here. Problem 6 is something most people in here need to work on. From what I remember grading, that was a bad spot.
And we needed that for problem 1.
Do that for problem 1 on the final or what?
We needed that for 1 on the take-home test, the first one. For showing the eigenvalues.
Oh, yeah, that is true. It was necessary. I mean, that is often necessary, this equivalence, right? But proving the equivalence and using the equivalence are 2 separate things, yeah? And, you know, there was all kinds of badness here. Like, you guys need to review how to make an argument like this. There was badness here. Lots of badness. But I have hope. I think you guys can get it. I have promised Hannah, in particular, that there will be a question somewhat like this. So that is a given on the final, that there will be a question to calculate the matrix of an abstract linear transformation with respect to a pair basis. Something like that will happen. Not necessarily this problem, but something like it. Oh, and I think I still need to write the solution to the last problem on this test. Yep, still the case. Or you could ask King, he has a solution. But I haven't checked his solution yet either. The isomorphism question.
Wait, so you still don't know whether you got a good score or not?
I'm still not sure if his score stands or if it needs to be revised. That's true. All right, before my computer reboots. I hope you guys didn't have more questions because we're out of time. Oh, you go ahead, though. Yeah.
On the final, like, if we get there a few minutes early, can we start?
If you get here a few minutes,
What time should we start?
when is the final?
12:30 Friday.
I think I have to give you guys. I think I have to give you guys 2 hours on the button because I've got a lot of different people taking a lot of different times, and I just can't be sure about extra time on all the slots. So I will try to be here on time so we can actually have the full 2 hours. But I will probably be somewhat picky about the ending time being actually the ending time.
What about the length of the exam? Will it be comparable to these, or will it be longer since this is a 2-hour exam?
It should be longer because it's a 2-hour exam.
But easier because you only have 2 hours.
But easier because you only have 2 hours? What?
Just make it easy.
That is why he is the president of the math club. That's right there. That's right.